Hola, buenas tardes. Buenas tardes a todos. Empezamos este...
Good afternoon, everybody. We are going to start the second afternoon round session with a slight delay. I believe all the speakers are already in the room. After consulting and checking it up with the speakers, excepting Rebecca. I couldn't ask you, Rebecca, because I didn't know you firsthand. But if you agree, we are going to start the workshop. The format will vary slightly compared to the previous format. First of all, we will introduce the speakers. Then there will be a Q&A session. And the next speaker will start so that we can stick to the original agenda. So, first of all, I'd like to give you a very warm welcome. Thank you very much for being here today. And without further ado, I will now introduce the first speaker, a very good pal of mine. He is a PhD student in the Carlos III University of Madrid. I had a brief script of what I wanted to say about him, but I don't think I can find it now. Oh yes, here it is. Juan González Víctor. He is the university professor, assistant university professor, lecturing professor of the electronic engineering department of the Carlos III University of Madrid. I am guiding his PhD, and he is researching assistential robotics, and this is the backbone of his thesis of his PhD. He participated in a European project in the field of robotics between 2007 and 2008, and he has been an active researcher in the field of robotic assistential cognitive robotics, and he has contributed in numerous open source software projects in which we try to free the source with different bookshelves that can be utilized in other platforms. Without further ado, I will now give him the floor. Thank you very much, Alberto. My name is Juan González Víctor. Today I'm going to introduce in this session the paper entitled "Give Me the Red Can, Assistive Robot Task Creation Through Multimodal Interaction." This has been written by Santiago Morante, Alberto Jardón, Carlos Balaguer, and Juan Víctor. Myself. We are part of Robotics Lab in the Carlos III University of Madrid. The system I'm about to introduce is the integration of numerous components with numerous channels through which the users in a domestic or home environment, they can do any daily home task with a robot. The platform, the test platform, these assistential robot that you see on the screen, it's the so-called Assibot assistive robot. I will talk about this robot first of all, then I will move on to the explanation of the implementation of the structure that allows the integration of the different components, and then I will move on to talk about the different components, the touch buttons, the automatic speech recognition, slide programming interface, nothing to be scared of, and the Wii remote controller. Finally, I will finish with the experiments and the outcome. The Assibot assistive robot, it's a medium to small size robot because it is designed to be used in the home environment. It is not an industrial robot. It is a robot to be used at home or in a smaller environment, assistential environment, with the aim of assisting people with dysfunctional diversities. It has two different anchorage points that can be connected to different wall connectors, floor connectors or ceiling connectors, and even in the wheelchair, thus being fed with the power of the wheelchair. It also has equipped different inter-exchangeable tools to help the users. For example, a razor machine, a toothbrush, or a clamp to grab things. With the Azipod assistive robot, we've studied different interfaces, and this is one of the best examples because we have managed to integrate with its open architecture numerous interfaces that come with built-in devices. Therefore, users can become acquainted with these devices beforehand. Integration uses the YARP communications with different ports, YARP, but most importantly, we manage a coherent integration of different modules. But most importantly, the web interface. This is a website that can be browsed with any device, either a tablet or a PC or even a smartphone mobile device. It only requires connectivity, and this is also integrated with voice commands and the Wii remote control. And this entails numerous actions that we will now describe. This is a snapshot, a screenshot of this web interface in a PC. At the top you can see numerous working tabs, and at the bottom to the left you will see the connection manager that allows us to connect ourselves to the simulator to do tests, or to the robot, or to both if we are willing to do so. At the very beginning you might find this slightly difficult with all these different options, but that is the reason why we have developed this task creator. This is merely a guide, an assistance guide that guides you through the different windows. Once you activate it, there is a progress bar to the right at the bottom, clearly telling us what we can do, the different options facing the user for that specific tab. Here, for example, we could move the robot motor, engine to engine, for example. Next window, we can move the robot in our Cartesian space, upwards, backwards, to the front, to the back. In every tab, you can either use the red button to record a specific space point, and afterwards this would be a passing or passage point to create different trajectories for the robot. But simultaneously we can provide another possibility, that is to use the Wii joystick, because we have an infrastructure that allows us to do so. That would be a video of the functioning of the Wii joystick. If we press this trigger button, the robot will move forward. If we press the other button, the robot will go backwards. At all times, the robot shall try and maintain the same orientation and angle. And also, we have certain freedom that allows us to rotate the base of the robot, as you can see on the slide or on the video. And simultaneously, as I said, we can record points, for example, for any given task we are creating. The next window displays programming. Don't get scared because of all the different codes. This is the expert mode, but it's as simple as that. We are out of the left menu, we just select where we want to go. So the easiest would be from 1 to 2 to 3, thus introducing close the clamp option, and then go backwards 3 to 2, 2 to 1. And then we will record a name to it. On the next window, speech recognition. Here we will record a phrase. For example, give me the red can, and the system will record it in a text or wording format. These might use a web format or a local format. And in the allocation stage, we allocate that voice command to the tasks that we have programmed. And we can also choose an icon to it. And we can link these icons to the actions. And the system will automatically recognize whatever we say. I will now, I will display the video afterwards. Now, I'd like to say that this system was tested with 10 inexperienced users for 2 days. And as researchers and professors, the outcome was a roaring success, because for 2 days they managed to do tasks that will take 2 weeks to do within industrial robots. All the users claimed that the interfaces were interesting and most valuable. They all found recognizable voice patterns, which means that the system does not always understand what we say. Sometimes we say, give me the red can, and the system will understand, give me the red cab. But because of repetition, we might find a pattern that the system will always understand, therefore always doing the same task. Now, regarding the controllers, there were 2 users who claimed that they disliked the Wii remote control. Perhaps our colleague Oscar can present numerous alternatives to the use of Wii controllers. However, we are, on the other hand, developing other types of systems, like, for example, bracelets that allow us to control the robot. Now, in order to use standard metrics, we use the system usability scale with an average punctuation of a 70.5%. Not bad, but there's still plenty room for improvement. The best point is that the users claimed, I would like to use this system frequently. However, the worst part was that they said that I would need the support of a technical person to use it. Even if this was beneficial, I will need someone that is techie savvy. Thank you very much indeed. I'm going to play the video, but please remember that all this development is open source. You can download it, execute it, especially the mock-up, the simulator, absolutely everything. The only thing that you need is a robot to execute the task. And that's because we are robotics. Thank you very much indeed.
Muy bien, pues muchas.
Thank you very much, Juan. Now we are going to proceed with a Q&A session. The interpreter apologizes, but I cannot translate the question unless they use the microphone. Perhaps Alberto can give me a hand with this. Okay, I can answer to this question then, myself. Azibot is a development platform allowing us to develop research in the field of usability, shared controlled, empowering the robotic system, and understanding the user's intentions and guessing those. Ideally, the platform would be as practical as possible. All the interfaces need to do something useful. We have a dummy on the video. You will see it in a kitchen. So the kitchen is a very complex environment which entails numerous tasks. And the robot needs to interact with different objects. For example, when you want to grab things that are so different as a glass of wine, a pen, or a mug. So the idea is that the robot needs to adapt to the different objects. The robot acquires the capacity to get a grip of the different objects, and it'll adapt the movements, and therefore in the future we will manage to assist in the accomplishment of numerous tasks. This is an open source system. Our effort at the moment is mainly focused on the base development, on the based technologies development, to benefit those that do not have a real technological background. That is the first result of this tremendous effort. The sequence of movements should be done by the users according to the needs and requirements. But we have to develop extensive technology, low-level technology before, in order to take a step forward with regards to what you just said. In principle, it's open source. But introducing robots in the day-to-day life of these individuals is no picnic. So the idea is to avoid unnecessary expectations. We still have many systems to develop. Any additional questions? I understand the goal of your project, but I would like to know, although I find this very interesting, how much does the robot cost? Yes, I know the goal of your project, to teach the robot. The robot is cost less. I can tell you how much money did we spend. More than 200,000 euros. We managed to do this with the assistance of a European project and the funding of a European project. The goal is not to develop new mechanical arms prototypes. No, at all. Because there are arms in the market that can do the same interaction as we do with Azibot, but the control interfaces are either completely inaccessible or not easily handled. The tools you can find in the market, we have purchased a commercial robot. Our goal is to adapt it to our software development. These type of tools might cost you 25,000 to 30,000 euros with no adaptations. Perhaps if you buy a second-hand robot, it's cheaper. Even the distributors of the manufacturing companies, they can sell you the same model for less than half. Any other questions, please? Then, if you agree, we will now move on to the following and next keynote speaker. And thank you very much, Juan, for your presentation. While the second speaker comes to the dais, I will introduce him. Teodiano Freire, a very good friend of mine. He's an associated professor of the electric engineering of the Espírito Santo University, Federal University in Brazil. He has a PhD in physical science in the Complutense University. He has worked with colleagues from the University of Alcalá and the FESIC. He is an associate researcher of the National Center CNPq, and he has extensive background in the field of electrical engineering, the use of mobile robots and industrial robots, rehabilitation robots, assistance technologies, biomedical signals of wide spectrum. He has published numerous papers and publications in different magazines, and he's the owner of numerous patents. Today we are so pleased to count on his collaboration to present the latest works presented in the field of assistance to recover mobility. Thank you very much. First and foremost, I'd like to take the opportunity to thank the ONCE Foundation for allowing me to come to present my work. My group comes from the Federal University of Espírito Santo in the city of Victoria. And for the past 15 years, we have been developing assistance technology with numerous prototypes that we have already developed in the past years. We have created lifts to move blind people around, the upper limb prostheses, robots to help severely affected children, to help children with autism assessing the brain signals. And for the past 5 years, we have been developing robotic wheelchairs that can be commanded with the blinking of the eyes, blowing, and even brain signals. What we are going to present today is the work we developed last year. It's an ongoing work. This is one tool that it's a robotic walker that can be used by people with residual movements. That is the robotic platform on the slide. The project is ongoing. We are still introducing changes, but what I will now show you, it's what we have so far, which is very useful from the physiotherapy point of view. This is much better than sitting in a wheelchair, especially for those who can have the possibility to walk around. And at the same time, this acts as some sort of rehabilitation. The platform has also sensors to capture parametric information regarding the way they are walking, and it can prevent arthrosis and other types of disabilities in movements. This is a very useful platform for numerous types of users. But most importantly, the platform allows users to be self-reliant and self-dependent. It has numerous sensors. The platform follows the pace of the user, the rhythm of the user. because there is a control system which is embedded on site, and we also have some strength sensors in the arms to measure the intensity of the movement, the input, and the direction. Do they want to go to the right, to the left, and everything has been controlled with one system which does all the processing of the sensory information. This is a brief display of the sensors and their locations, and the walker that appears on the slide is very useful, as it has one peculiarity. It has like some sort of a forklift truck. The person can sit down and be lifted. They can be seated or walking. In order to facilitate the movement, but also sitting down and getting up, which is one of the needs of these type of individuals that cannot walk without assistance of a cane or a walking stick. These are additional details. The platform goes into the platform, and it measures the distance of the legs. The different strength sensors capture the motor intensity. When the person starts walking, the sensor will help them. This is much more than a mere walker, because it allows you to ramp up and down, and it also allows the person to stop. If the person stops, the walker will come to a halt, because there is an entire control structure that can handle this data.
This is the sensor that we use. It's highly precise. It can determine the sensitivity of the legs in a very precise manner. And from that analysis, the system manages to infer information, not just the stability of the legs, but also the orientation. If the person, when trying to turn, makes a certain angle, this is detected, and this is entered into the control system, thus enabling the walker to adequately analyze movements. There is a block diagram that shows this, and there's a series of equations that use this data to create the movements, which is in the end what the walker requires. The walker takes the sensory information to determine the linear speed, the angular speed for the user too, and this enables the walker to assist the person to go in the direction and the speed desired by the user. This is the model for the platform. Here we can see angles and distances. The model takes into account modular parameters and speeds. And what we intend to do is to use the movement to develop the distance between the user's legs, and we want to reduce the error to 0 and the vector that specifies the movement of the person to have an error range of 0. So thus we want to modulate everything and to use this non-linear model to set up a control analysis V sub D and W sub D to generate linear and angular speeds that match the march of the user. This is done on a theoretical basis, and we can determine the errors between the angular and linear speeds. This is something that we want to show. We have carried out simulations in difficult situations. This is the robotic system that we are showing on the screen, and here we can see a circumference or a circle that shows the dynamics of the system. These are the curves In reality, what it means to say is that this is the system dynamics, and it shows the support provided by the system. There's a tiny error that we can see here when the curve is more closed, because this is a kinetic approach. It shows how the march is being tracked. On this robotic platform, we do not only use a robot but also a person. We therefore take into account and observe security measures and safety measures. We don't want the user to crash against the walker. So there are many issues that we take into account in simulations that encompass the walker and the user. We have movement sensors used to send commands to the device, and also, for instance, if the person is not putting his or her arms on the armrest, the walker won't move. If there's too much pressure put on the walker, it makes the user stop. So there's a series of security features that are being implemented in accordance with the information received from the sensors. This is the physical rehabilitation center that we have in the state of Espiritu Santo. We used a series of volunteers. We applied inclusion and exclusion criteria, and from that point on, we managed to carry out experiment with people who were interested in this and that experienced different sorts of problems. We've obtained parametric information regarding march. We also set of parameters for people with arthrosis or other issues. The movement parameters of the users have been gathered because there's a system in the onboard computer of the interface. We register all parameters and then we process them. In the case of individuals, of the volunteers that we had at the center, we had a lot of signals that haven't yet been processed and therefore they haven't been issued. But the idea is to use healthy individuals and to analyze the way they walk and to compare them with other people that don't have a normal march, so that we can obtain parameters and to apply them to different groups and thus to contribute to the adequate diagnosis of people who have a certain pathology or problems when walking. These are real examples that have been carried out in our laboratories and even outdoors also. The video at the top of the screen shows how this person is using the walker. In this case, they're using an inertia sensor that's wrapped around the waist of the person, because this is the control system for this case. But this goes to show that once you have the information regarding the leg distance, we have this. But without having information regarding the direction of the person, the walker just follows a rectangle and he follows it quite well. This entails that the control system is working. At the bottom side of the screen, we can see a simulation carried out outdoors. So this goes to show that it can be used indoors and outdoors. This platform is very useful for enabling mobility for people. There's a lot to do still. We know that we can improve some aspects in the platform. We need to carry out a new test. This is not a product, it's a prototype, but our idea is to make something which is even more robust. We are undertaking a new project right now. We're starting off, and our idea is to put together the robot walker with a prosthesis, because some people could walk but they have knee problems, for instance. So we have an orthesis, so the speaker. It's a simulated orthesis that can help the person walk. We also take into consideration brain signals and biomechanics, because the motor system has to do with the biometric sensors that we already used in other works. This is a new piece of work. It's still promising because it has yielded very good results. We're working on it, on also improving the control system, implementing dynamics control so that we can obtain better results. But the people who tried it already stated that it's easy to use. Sensors collect all the information, and the user's statements say that it reacts quite quickly, that it doesn't interfere with their movements, and that it's actually quite useful. This is what we wanted to achieve. We need to implement parametric information on the user so that we can solve certain types of problems that people may have when trying to walk. This was more or less what I wanted to present to you, and now I'm open to questions. Thank you very much.
Muchas gracias. Vamos a abrir un turno de preguntas.
There's a Q&A round if you want to pose questions. The interpreter apologizes, but the speaker is not using a microphone.
Mira, nosotros ya tenemos experiencia.
We already have experience with the wheelchair on the basis of research that we carried out at the lab. We wanted to reach the market. This system has already been patented, and my colleague is a co-author of this piece of work, and I think he could answer more clearly. What's your estimate? When do you think this platform will be marketed? The first version of this, for this walker, is something that they have been doing from CSIC since the 90s. And in my PhD, I also tackled this issue. First of all, we need to collect signals to provide safe assistance, because we wouldn't want anyone to trip and fall. So the first thing that we do is to make sure that there's active safety implemented. There's a difficulty because sensors which are integrated in the wheelchairs are quite expensive. So the first version of this walker aimed at having a better commercial solution, reducing the cost of those sensors that cost $10,000 and reducing that to $100 or so. We obtained a lot of information, but we considered that possible, and we undertook a master's thesis to try to tackle this problem. And I'm sorry for taking so long to answer your question. Now, in terms of marketing the services, I must mention the experience that we've had with another product that's already being sold by a company. It took us about 8 months to obtain a functional prototype, and validation, which is getting ready for the market, took us 4 years. This is an example that I'm trying to give to you because we had a company which is interested, but this interest also requires that they make an investment, even if we do everything ourselves. We play our role, which is to create the science or the information, and then through a patent you can transfer this to the technological level. That took us in the past 4 years. Again, the interpreter apologizes, but the comments are being made without a microphone. It's a device that makes a person stand up, and then it allows the person to move. when we had that ready to get to the market, we had to reduce cost. We had to fine-tune the manufacturing so that everything could be put together here in Madrid without importing the parts. And that took us 4 years. And even color matters, which is something that researchers don't take into account. Someone tested it and they said everything looks rusty because it hadn't been painted, or there was a cable that was visible, and they were saying that you could get electrocuted with that. So you need to have everything very fine-tuned, because when you buy a car or a bicycle, it's painted and it looks nice. So it took us 4 years to make the adequate preparations so that this could be ready to be introduced in the market. Thank you. Thank you very much. Any further questions? I just wanted to clarify that we're from Brazil, but we did our thesis here in Spain, so we have a lot of allegiance with Spain and a lot of agreements which are in place. Thank you very much. Thank you very much for being here, to you and your colleague, and please put your hands together for our speakers. We're going to have the next speaker now, who's Rebecca Corralejo Palacios. She's a researcher at the Superior Technical School of the University of Valladolid. She is the author of international national works that have been made public in magazines and in different research projects. And I know that she's obtained very good results in the field of brain computing. For instance, in July, they received an award from the Castor Foundation. And this is not the only one, nor the first award that you've received. Thank you very much. You have the floor, Rebecca. The piece of work that I'm going to present to you is entitled Developing an Application on Computer Interface based on P300 for the assistance of people with a serious impairment. I will make an introduction. I will tell you about the objectives of this work. Then I will describe the materials and methods used. And finally, I will present the application that we have developed, the outcomes, and the main conclusions. First of all, I would like to say that this is a brain-computer interface, BCI. It's a system that monitors brain activity, and in a certain manner it translates these brain waves into commands that intend to control a device. This device could be a TV, a computer that we all have at home, or it could even be applied to wheelchairs or prostheses and others. In order to guarantee this, we use EEGs. This is a non-invasive technique. As you can see in the image, a hat is put on the subject's head, and you apply a gel, which is similar to hair gel, and the equipment required is quite simple. It's cost-effective, and it enables the amplifier, which is what you're seeing up here, to be quite portable and easy to use. The goal for BCI systems, the final goal for them, would be to improve the life quality of people with impairments so that they can increase their self-dependence. The objective of this work is to apply BCI based on P300 potentials to enable the control over certain electronic devices which are normally present in a household. In the picture we can see the specific devices controlled by this application, namely a television, a DVD player, a multimedia disc, an audio equipment, a telephone, a light bulb, a heater, and a ventilator. So what is a BCI system based on P300? Well, it's a BCI system that doesn't require training. Some other systems do require a long training stage so that users can come to know how to control certain brain activities. In this case, the P300 systems harness a specific stimuli. This happens because when you mix an unexpected stimuli with more expected or frequent stimuli, we can see a peak in brain stimulation, which happens about 300 milliseconds after the stimuli. This is what it's named after, P300. So if we detect that peak in brain activity, we can use it to control certain applications. The most widely known application for this system is writing. It's for selecting letters and number. We have a starting matrix, which is the one that we can see on the image. It has 6 columns for different character types and numbers. So the rows and columns will increasingly identify and flash and turn into white in a random manner. What the user has to do is to position a letter. For instance, we can select the letter T. We need to focus on letter T, and we need to count how many times it flashes in the second row, in the second column, or the 4th row, which is where it is located. We can see how they flash. So mentally you need to focus on letter T, and you need to count how many times it flashes. It is quite more likely for another column or row to flash than the one containing the letter T. So whenever this happens in the brain activity, this potential would show. If we are capable of specifying in which row or column this potential was caused, we can know on what letter or what specific option the user was focusing on. This type of application is something in which we have replaced the characters by images representing different devices. So the idea that we are going to use is more or less the same. It is a row and column approach. So by focusing on the item that we want to select, it will be possible for the computer to identify it and to carry out the action. These are the materials that we use for this purpose. First of all, we use the EEG, a biometric intensity measure machine, and also other EEG channels, 8 channels namely, that have to do with the occipital cortex, which is where this normally shows. In this research studies, we used active electrodes that enable us to quickly position the cap and to receive better signal intensity. So in order to validate this application, we engaged real final users, which is to say people with a certain degree of impairment. We engaged 15 users of the reference centers for discapacity and for disabilities and impairment. They all had motor impairment from minor to serious and caused by different pathologies, brain paralysis, multiple sclerosis, and others. Many subjects also have a cognitive impairment ranging from minor to serious. This is important because BCI systems that require training are limited by the cognitive capacity of users. In this research study, we were interested in finding if this type of impairment can limit the development of these systems in terms of adequacy. For developing this application, we selected devices that are normally present at a household and that would enable a certain degree of comfort to control the temperature and illumination in a certain room. It also has to do with communication points, so that we can make calls, and also we can control televisions, DVDs, and audio systems. The experimental protocol was made up of 3 sessions, a calibration session that intended to adapt the classifier to the specific response of each user. Subsequently, we carried out 2 assessment sessions. In these sessions, users interacted directly with the app that we had developed, and they controlled the devices. What we did is to propose a series of sequences to them and to measure how precise they were in doing them. For instance, an example of sequence would be accessing the fan menu to activate it, and to program the timer for an hour. In this picture, we can see one of the users undertaking these tests. These are the results. We have an application that enables us to control the device that I mentioned through the P300 system. In order to do so, instead of only having one single letter matrix, we will have various matrices. One will be the main menu, which is the one that we are showing here, and then an extra matrix for the specific features of each device. So if we were to select the TV and to access its control menu, we would focus on the TV image, and mentally we would have to count how many times the TV flashes. In this case, instead of intensification, as we did in the case of letters, we use attenuation because contrast was less of a problem. We can see the effect of an attenuation. Within the device, we will find a specific menu. In the case of the TV, the menu would be the one with the red background. There we can carry out the different features offered by a TV remote. We could switch to a specific channel, we could browse through the configuration, and so on. The second menu with the blue background would enable the user to control lights. This is a light bulb that can change colors. You can turn it off, you can turn it on, you can select intensity and color, and so on. The other menu, which is the one with the purple background, enables the user to control the multimedia disk. Through the arrows, the user can browse through the multimedia content or access the previous or next picture or the previous or next movie to activate or deactivate subtitles, and the one with the yellow background would show the telephone control menu. It would enable us to dial each digit of the number that we want to call. It would also enable us to repeat the last call, or to call 911, the emergency number, or 112 in the case of Spain. And it would also enable us to access the contact list that would contain a series of pre-stored numbers. Also, all menus include the option of going back to the start menu, so that a user can enter in and out of a menu and they can resort back to the start page. Now, regarding precision outcomes, after the calibration session, half of users were capable of obtaining a 90% precision rate. This is something that we had to repeat for 2 subjects only. One of them was because he didn't understand the task in the first session, but in the second session this person obtained an 80% accuracy. And for another subject, we had to repeat the session up to 3 times, and it was not possible to create a classifier. We realized that there were many artifacts in the EEG calibration because the user had a lot of spasm, was too spastic. So the reference was distorted in those cases, and this affected the whole registry. Now, regarding the assessment sessions, out of all the users that undertook them, 9 of them obtained over 80% precision or accuracy, and 5 of them were above 95%. 4 subjects obtain moderate accuracy. Possibly we would need a further calibration session with a more robust approach to calibrate this device adequately for them. There was only 1 subject for which the classifier couldn't detect the potentials, and thus it couldn't configure the application adequately. By way of conclusion, we have managed to develop an application that enables users to control the devices which are frequently present in households, and up to 113 control commands can be made through this application. The application has been tested with a wide population, and I say wide because for the normal development of these studies, we could say that this is wide. Nevertheless, it's only taken on 15 subjects. We consider the accuracy to be quite high, as it is over 80% in average. And it is very important to mention that the type of impairment or the level of their impairment didn't impact their ability to control the application, because if they have serious motor impairment or cognitive issues, they still managed to obtain great accuracy. So this type of BCIs would prove to be very useful for applications that increase autonomy or self-dependency and improve the life quality of people. Regarding future steps, we want to widen the research population so that we can take into account people with different type pathologies, degrees, and levels to evaluate up to what extent it would be useful, and so that we can adapt it to their specific needs. It would be also simple to include extra devices in the application, implementing an interface for certain protocols for domotics, Wi-Fi, Bluetooth, and others. And also, we are assessing the possibility of using this electroencephalic signals to detect whether the user is tired and needs to rest, and also so that we can stop the application, of course, and to determine also at what point the user wants to gain control over the application again, to do this in an automated manner using the controls that we have in the main menu. This was my last comment, and I'm finishing my presentation now. Perhaps there are any questions? Yes, we have a Q&A round now.
Buenas tardes, soy Javier Muguerza de la Universidad del País Vasco.
I come from the University of the Basque Country. Congratulations, it's a very interesting research. I wanted to ask you a couple of questions. One has to do with the accuracy estimation. Could you delve deeper into how you estimated the accuracy? Were you abiding by a series of objectives, and you were measuring whether or not they were successful in carrying out the task or not? And also, when you talk about classification, what type of paradigms did you use to classify the signals obtained from the system? In terms of accuracy, what we did was to propose a series of sequences with a different length. As I said earlier, they had to access a menu, select a series of commands, go back. So what we measured was the accuracy, selection by selection. And in some cases, the sequence had to be dynamic. That is to say, if you wanted to access the fan menu and you accessed the TV menu, you had to go back to the start page and then try again to access the fan menu. So accuracy is calculated upon that dynamic sequence. So item by item or selection by selection. Did I make myself clear? Yes? Okay. And now, as for the classification, we use a linear classifier, which is simple. What we do is to use calibration data to select characteristics through a step-by-step linear discriminator. So 60 features are selected, and they provide a certain location that specify in which channel and at what moment it becomes clearer where the potential is. At the end, we obtain a certain probability regarding the field and the column that resulted in that potential. And that is how we check the option that was selected. We have a further question.
Hola, sí. Tengo...
Hello, I have a question and a comment. The first is that we have developed BCIs in Brazil too, and we have the same problem, which is the cost of the system, which is quite expensive. What was your motive? We want to use this for children that have autism and to measure their emotional stability. We realize that it's quite suitable, but it costs 800 euros. My question is, did you try to use this as a leitmotif? We haven't used it, but we got the chance to get to know it, and it is true that it doesn't have the standard positioning that an EEG has. It is located more on the external surface where they position these sensors, and we noticed that the signal registered has to do with movement more than with brain activity. It detects winking or facial gestures, but I don't know if it's adequate for brain activity. Yes, we're using this for brain activity. For visual issues, we are using this device for the parietal lobe, and for the visual region it works. We also came across the problem when we were dealing with the chair. The issue is when to start simulating and when to stop. We use DRS patterns. When the person wants to stop using the system, they can close their eyes. We can check the brain pattern and the alpha pace, which is increased by 5. And when the person wants to finish, they close the eyes once again. So for starting and finishing, they close their eyes, and we obtain the pattern. This is the problem or the constraint that we find, which is how to activate it and deactivate it without depending from another person. Thank you very much. Are there any further questions in the room or any comments? I do have a question myself, if you'd allow me, Rebecca. It has to do with the level of acceptance or rejection. Do people want to wear this cap with so many cables and so on? Because you've tested this with real users. So what was your experience along those lines, in the sense of the rejection that can be foreseen when having to wear such a cap? The experience that we've had with the users in this center has been quite positive. I don't think anyone didn't want to participate because of the appearance of the cap. And now regarding the electrodes, I'd like to say that we've had other systems that were worse and people still participated. So according to my experience, people are willing to try and to participate. A different issue would be for them to be willing to use it in their daily lives. As it stands today, we should make it wireless. We should eliminate the gel issue. Yes, he was talking about emotive, which is apparently a solution. It is wireless and it's more static. The interpreter apologizes. The comment is being made without a microphone.
Lo estás poniendo difícil, sí, sí.
This is a difficult scenario, yes. Any further questions? Without further ado, I would like to thank Rebecca for having respected the time allocated to her talk. And since we're at it, let's give her a big and warm applause. Just to conclude the session, I would like to make a couple of comments. We are trying to be more centered, more user-centered, and this is the leitmotif that pushes us forward when working on all the different aspects that we want to cover. And of course, without people, we wouldn't be doing anything. We wouldn't have our motivation. Thank you very much.